I'd now like to introduce our second speaker. This follows nicely on the heels of all the images of Great Britain and Ireland. Our next speaker is James Cheshire from the University College London. He's probably one of the few folks actually leaving London at this time rather than going to London. Maybe he's happy about that, I don't know. So James is going to speak to us about CyberGIS and urban data. He has expertise in advanced spatial and statistical programming techniques, visualization of population data sets, in particular, a map of life expectancy and child poverty as mapped onto the tube lines in London. Is that right? He teaches master's level courses on geographic information systems and science, our programming research methods. He's the secretary for the Royal Geographic Society, GI Science Research Groups, and we look forward to hearing from him today. Thank you.
Thanks. So today I'm going to talk a little bit about some of the work we do in CASA, the Centre for Advanced Spatial Analysis, and mainly looking at urban data, so urban data feeds and so on. So I'm just going to give a quick outline or a single slide on who CASA are, for those of you who haven't heard of us, and then run through a couple of research applications, really. And I've split this into two different types. What I call traditional data sources, largely demographic data. So these are the sorts of things like the census, collected meticulously and carefully over generally long periods of time, perhaps, and at great cost. And then the second set of data I want to talk about are these new data sources we're getting, and the focus here will be transport feeds. And then the final section of the talk is just going to focus a little bit on what CyberGIS can do to help our research. So just quickly, our Institute kind of looks at all kinds of things, really, and we're a mix of computer scientists, physicists, mathematicians, geographers, planners, architects. So we're a really interdisciplinary group, loosely bound together, I guess, with interest in smart cities, visualization and mapping, urban modeling and simulation. One of the other great talents we have, Mike Batty, the chair of the department, has, is acronyms, and we've got all kinds of complicated acronyms here for the various projects we have. But one of the words you'll see repeated there are words like cities, complexity, simulation, geospatial, and so on. So we are really interested in almost sort of sensing the city in many ways and utilizing all the data we can get. So just going to talk briefly about traditional data sources and something I'm particularly interested in here, which are geodemographics. So the focus of geodemographics research is simply the analysis of people by where they live. And it's been happening for over a century. The late 19th century, Charles Booth did a geodemographic classification of London, for example, first of its kind. And so this isn't a new field, but what is new and what is the sorts of things we're looking at developing are things like bespoke classification. So traditionally, you would have a single classification for a whole country. The tapestry one from Esri, we have mosaic by Experian in the UK. And the problem is these aren't necessarily flexible enough for your particular applications. And so if you're interested in crime or health, the variables you put into those classifications are going to vary. Equally, if you're local or central government, if you're a local government, you want a geodemographic classification for your specific area. So we're developing applications where you can specify the variables you want and then create your classification straight away. But to do this, we need to cluster the data very, very quickly, almost on the fly. And also, we want to develop ways of expressing uncertainty in the classifications. And traditionally, in cluster analysis, this involves, multiple iterations of an algorithm to get some kind of p-values or something. Both these two things require a tremendous amount of computational power, and so we're really struggling to do it just on a desktop machine. Equally, you can look at integrating measures of spatial relationships, such as and pairwise comparisons. Again, these things are incredibly computationally challenging if you have, in the case of the UK, 220,000 output areas, for example, as your base geography. So if you're comparing one output area to another, that's 220,000 or 220,000 squared or whatever. So it's a very large number. So it all require large-scale computing. A particular area of interest for me, and it's what I did my PhD on, was looking at people's surnames and the spatial distributions of names across a country. And a way you can typically do that is to compare spatial distributions of one name versus another. And if they overlap in some way, you can hypothesize that somehow they were related, culturally related. So certain groups of names emerged at the same time in certain places. Now, this is some research I did on the Czech Republic, looking at networks of names, and it involved 200 million comparisons. So there are something like, you're looking at the number of spatial units in the Czech Republic that you happen to input into your analysis and multiplied by the number of surnames there are. And in order to get to 200 million, which is the sort of the manageable amount that we could handle, we had to create all kinds of almost arbitrary cut-offs in the analysis to say, well, we're not going to include names with a frequency of fewer than 100 bearers, for example, simply to cut down the numbers. And even in that long tail, there is information, and it would be really great in future to incorporate that in some way. Now, within this big kind of cluster graph, you can begin to identify clear population groups that emerge simply by identifying areas of spatial proximity. So in this case, this green cluster here are all Vietnamese names. We haven't labelled them as such. It just so happens that Vietnamese migrants into the Czech Republic tend to live in the same places. And within this big graph, you can identify different groups. Now, of course, the challenge here is twofold. It's both a visualization challenge, it's also a data mining challenge once you've created the graph. Another thing we can look at is changes over time. Now, this again is not a new thing. This is an image I think that Waldo Tober sent Mike in, and it's hung up in our office, and it's of Ravenstein's currents of migration in the UK. Now, this is particularly interesting to me because, as you'll see in the next slide, there's a close relationship between, or visually, this looks very similar to something I produced using surnames. So the processes, though, that go into creating this map were clearly very different at the time, and this involved some kind of meticulous manual observations of a relatively few number of samples, hand-drawn onto a map. Whereas what I do is I just take a large computer and a large data set, and I just inductively run it through and hope that you get something that's plausible. So this is quite hard to see, but these are shifting surnames between 1881 and 2001 in the UK. The majority of names actually didn't move very much, but the slight shifts are very close to some of Ravenstein's arrows. Now, the question is this any better in terms of the information compared to the very sort of almost deductive manual work that has been undertaken previously? And I think this depends on context. I mean, if you're out to show migration, then I'm not sure that this is any clearer in any way. However, if you're interested in particular genealogies of individuals, or we make linkages between genetics and surnames as well, then this information is actually very invaluable, and it could not have been generated previously because there are something like 15 or 16,000 arrows on this map. Now, behind this is a database, so if you're a researcher and you're interested in a particular name, you can search for the name on the database, and this makes things much quicker and much more efficient than the previous, what came previously, which was simply going through telephone directories and almost doing the maps manually. So this information came from the electoral roll, and we can use things like censuses and so on. What I'm going to turn to now is some of the new data sources we look at, specifically ones of transport, just to show the sort of information that comes through to us on a daily basis in CASA. This is a map that's in the National Geographic of the cycle hire scheme in London, and it depicts one user's journey over 12 hours around the city. So cycle hire is something that has come to many cities, and you can see here it's a big deal looking at the number of bikes. The Chinese are leading the way with this, with the largest scheme having over 70,000 bikes in it. London's pretty humble by comparison, at 7,200 odd cycles. New York's going to, I think it may have, if it's not already online on stream already, it will soon be 10,000 odd bikes. So because these are all new schemes, then they're well networked and there's big databases behind them, and we receive the data in two ways. We can take the docking station status, so this is how many bikes are in and out of a particular docking station when you drop your bike off, and this is a continuous real-time data feed that we collect, and it provides a good overview of the system, so it shows you where docking stations are emptying and where they're filling up. The second piece of data, which is more detailed, is the individual trip data. So that gives the start and the end locations of the users. Now, because this is slightly more sensitive information, it's released periodically rather than, it's not continuously available. But from this we can derive flows in the system. So we've been collecting data from cycle schemes around the world now for just about 18 months or so, and we've got 1.5 billion rows of data. So again, these things generate a huge amount of information if you mine it or mine for it correctly. So one of the interesting things we can look at is the morning rush hour or the morning commute. So smaller circles are emptier docking stations, bigger circles are fuller ones, and if this is running now, I think I've just hit pause, play that again. You can see this is starting in the evening. As the morning progresses, people are moving into central London with the bikes, they fill up, and then central London gradually empties away again towards the evening. Now, this information is useful because it's extremely annoying if you can't put your bike somewhere because the docking station's full, or you can't take your bike, or you can't take a bike out because it's empty. And this presents a big redistribution problem for the operators. Now, I think it was Paris that first discovered that you need these vans driving around to redistribute the bikes because they realised that people don't like cycling uphill. So if your station's on the top of the hill, people are happy to ride down it and drop the bike off, but they need to bus or drive the bikes back to the top of the hill, so there's plenty at the top. In London, it's slightly more subtle than that, and you end up with things like shifts in the weather. So if it rains during rush hour, your bikes aren't where you want them to be for the next rush hour in that case, because they're still on the outskirts or in the middle. And we can begin to tease out these daily patterns around the world, and you won't be able to read this. I can barely read it myself. So this is Barcelona here, and what's interesting about the Spanish cities is they all go home at lunchtime. So you can see a drop in the availability of bikes in the morning, a drop at lunchtime, and then a drop in the evening. London is this one, and it's your textbook commuter city, really. So you have the two drops in availability of bikes when people are commuting to and from work, and then at the weekend you have this nice gradual increase in the usage towards the afternoon. Other places with flatter lines tend to be used more by leisure users and tourists. I mean, Vienna's another good one here. You don't get the morning and evening peaks. What's interesting is Washington started off as a kind of leisure usage scheme and is gradually transitioning towards a commuter-based one. So more and more people are using the bikes to get to and from work as time goes on. And with the individual trip data released, we can begin to guess the routes that people took and identify particular patterns or clusters in the city for particular routes. So I've taken this information for London and we've combined it with things like air pollution data, and it's being used in modelling exposure of cyclists to air pollution and so on. And again, what's interesting, London's now been extended. There's now, to the east, a smaller part of the scheme. But you can see how Washington, for example, almost operates two schemes in one. So that's people cycling. The next range of data we collect are looking at these things called Oyster Cards, which are the touch cards that people use to get on and off the subway system. So this gives us about 4 gigabytes or 17 million records daily. So this is a feed that's provided by Transport for London just to CASA, and we're collecting this at the moment over the Olympics. And we were kind of hoping that it broke, the system broke, just to see what would happen, because it might be interesting, but it seems to be holding out so far. So looks like Transport for London have done a good job in keeping people away, apart from those going to the Olympics. And this data gives us the entry and exit station for each person. So we know where you get on and we know where you get off. We're not sure how you get there in between. So in some cases, there's only one way you can go. But in other cases, there could be 1 or 2 lines you get on. And there are some data quality issues. So we've discovered that some people seem to be simultaneously exiting stations at opposite ends of London, which may have something to do with the IDs associated with the cards that we're looking into. And again, in a similar way to the bikes, you can see green big circles here are exits and red ones are entries, and you can clearly see the morning and evening rush hour. And looking at flows of people through the system, I mean, the interest here is if you break the Victoria line, what will happen to the Metropolitan line in terms of usage? Will people divert their journeys? Will people get on buses? Will people use the bike share scheme? So the busiest days for bike share are when there's a tube strike. And for Joy Division fans out there, here's looks like one of their album covers, but this is every line, every station on every line graphed entries and exits. I think it flows through each station, and again, you get the morning and evening peaks. But actually, the magnitude of those peaks and so on is interesting here. So it basically presents a huge data mining challenge, this. I mean, we've got all these journeys. How do we extract things that are meaningful? So we're tracking people, or you can track people through the network, but what about the trains that they're catching? So again, there's an API for this, which is based on the train signalling systems. We've got the location of the trains between track points, and again, this is giving us about 2 gigabytes of data. We've got it nationally. Again, the challenge here is that the data need cleaning during and after collection, and it's a real-time data cleaning problem. So with another animation here, look out for the flying trains. You can see them whiz across. And this again is where the IDs of each individual train are being moved around as they arrive to us at the API. So how we know whether a train's ID has been misassigned because there's a problem. What worries me most is that this is the same system I think they use to run the network anyway. So where you've got flying trains and things like that happening, and again, this is actually quite a clean version, it's very hard to us to try and establish what's going on automatically. If you look at it, you can see there's a problem, but doing this in an automated way when you're collecting this every 30 seconds is much more of a challenge. And just recently they've released a similar system for the London buses. So again, it's plugged into the departure board information. So every bus stop in London, you can text a number or look on the website and it'll tell you how long the bus is going to take, but also they'll give you the boards. And there are 114,000 bus routes completed each day in London, so that's a bus going from origin to destination. GPS information will be released soon if it's not available already. We don't yet know passenger information, and of course the problem with buses is that you know where people get on, but you don't necessarily know where they get off because they don't have to touch their card anywhere. This isn't very clear, I'm afraid, but this is the density of the bus routes through the city, And you can see it gets highly concentrated in the middle, and this is this area of Aldrich here has something like 6,000 buses a day pass through it. So you can imagine if there's a problem on that particular piece of the street network, what will then happen to the surrounding areas where the buses get diverted to. And we can see what happens if there's a bus strike, for example. So on the left is your normal day, and on your right, the bus drivers had a strike. But you can see here, there's a clear east-west split of the city, which coincidentally matches where some of the richest and poorest people live. Richer people tend to be in the west, poorer people tend to be in the east. Sorry, they're more reliant on bus travel because it's cheaper, and parts of this, especially parts of southwest London down here, is very poorly connected on the London Underground network, and so all these people here were actually doubly disadvantaged in a way, because if most of the drivers had gone on strike in West London, then people would have got other forms of transport that are not available here. And so this is simply because some of the bus companies so there's not a single bus company operating for all of London. There are something like 3 or 4. And several of the bus companies, namely the ones that serve the West, went to court and managed to ban the drivers from going on strike, whereas those in the East didn't manage it. So that explains that split. But again, because we've got so many feeds of information coming in, we can begin to establish how, if the buses break, how will the London Underground cope? And we're beginning to draw these feeds together with this thing called City Dashboard. This is, I think, yesterday. It's citydashboard.org. And we have, basically, this is a front end to most of our feeds. So we've got everything from the weather to air pollution to, we've got a Geiger counter, just in case anything happens. This is quite amusing because we have these little GPS tracker things as well that some people have been using to look at people through the city. And if you plug them in to the computer that's running the Geiger counter, this goes berserk because it's the same data format. So we had numbers into sort of 300 here, so we had to pull it out quickly in case people got concerned. But we have here like the Twitter trend, so we're always collecting social media data, which I'm not going to talk about. And also some cool stats about the number of buses, underground trains and cycle hire cycles on the roads. So this is all very nice, but what does CyberGIS have to offer? And where is all this data taking us? The first thing, and I mean, these are themes that have been repeated, I think, over the last couple of days, is desktop GIS just isn't up to it anymore. When I first started my PhD and started doing GIS in Cheshire about 4 or 5 years ago, desktop GIS, I'd say 50% of people were using it on a weekly basis. Now, I think that number's dropped to 20% as people are, especially, I mean, I'm the same, I use R and Python now. I very rarely have to open a desktop GIS to do anything, simply because they interface much better to the likes of MySQL and PostgreSQL as well. In the UK, at least, there's a trend towards the increasing recruitment of computer scientists at the expense of geographers. So these people can code the languages I've just listed, but they don't necessarily get the applications as well as geographers, or perhaps the broader context. I mean, I would say that because I'm a geographer, but I think sometimes, you feel you're having to fight a bit of a battle about how it is that some of the data is being collected and applied and communicated. And equally, we feel that there are other departments within UCL and beyond, especially computer science, that are increasingly encroaching on the areas that we've been doing for years, smart cities, for example. One thing we haven't talked about here is so much as quality outreach, and I think CyberGIS has a lot to offer here, especially with web interfaces. So that the tube map that was mentioned in the introduction there was extremely popular, and these are the number of hits to our website. And all we were doing was serving static tiles, and we hit 6,000 hits in 1 hour. So Yeah, so that's one thing to bear in mind. And the second thing to bear in mind is that the average time spent on the website was 20 seconds. So you're dealing with two things here. You're dealing with a huge quantity of people, but they've got a very short attention span. And I think it would be really nice to have some kind of interactive interface. There were some people questioning how I'd calculated or done the averaging for the life expectancy at each station, and it was based on a static buffer operation. I'd done a 200-meter buffer from each tube station. I would have really liked some system where people can put in, 100-meter buffer, 20-meter buffer, 300-meter buffer or something, and seeing how the results varied for themselves. But there's no way that without a large cyber infrastructure behind the website that it could cope with 6,000 people trying to query that information. And the other thing that is interesting is, of course, you're very popular for a few days and then you're soon forgotten. And so some kind of infrastructure that's flexible in terms of, farming out processes to multiple machines and then bring it back in again to one or two, again, is something that CyberGIS I think would be very good at. So these are kind of things that I think are interesting research challenges and where CyberGIS helps. I mean, we've talked a lot about collection, storage, description, nice maps, collecting lots of data, and we just talk about, we describe what we see. There's not been a huge amount of analysis on certain data feeds. Social media is another good example where you haven't yet reached the point we've reached with the traditional data sources, and I think that's partly a limitation of the computational power we've had available to date. And we want to actually get a bit more towards prediction. So our city dashboard is saying what's happening now, but we'd be really interested to know what happens in an hour's time or 2 hours' time, or some kind of scenarios where if the London Underground were to break, so if, Victoria Station were to be out of action, you want to intelligently redirect people around the station. But the problem with the London Underground is there's not a reliable cell phone network on it. So there's no good telling people 1 minute in advance, which is what now happens, that Victoria Station's out of action. You want to be informing people before they get on the train how best to direct people around. And again, I think there's a lot to offer here in just simply getting all the data we can and processing it. So that's me done. I've just got a nice picture of the Olympic rings on London Bridge. It would be a shame not to mention it. And some thanks to some of my colleagues. Thank you.
Thank you, James, for a fascinating talk. We have time for a question. You alluded to this a little bit in the second to last slide, the types of things that you might look at if you had more computing power. What are the kinds of problems that you've seen when you mentioned people going from desktops to non-desktop environments? What kind of problems have you seen drive that?
Well, I mean, some of the desktop, it's a combination of problems, really. I mean, you're obviously limited by hardware. If you've got, 10 gigabyte data set, there's no way you can efficiently load that into RAM or something unless you've got a very large machine. But also I think for a lot of what we do, there's an increasing amount of bespoke programming required. So instead of loading up your entire GIS that does about 500 things, the more modular approach, and this is why I think R is very successful. It's a very small program and you just simply tell it, or you just add on the things you need, which means it runs much more effectively, I think. Things like interfacing to database is incredibly important, but also just the flexibility of having a single database that can be central to your department and multiple people can access it in whatever software they choose.